Hello everyone and welcome to this video. In this video I'm going to do an example with beam elements in Excel using the stiffness method. And this is the problem I'm going to look at in this example. As you can see, it's just a normal beam. It has two elements numbered, 1 and 2, and also 3 nodes. You will also notice node 2 is 10 millimeters below the beam, but I'll get to that in a moment. And the Young's modulus for the beam and the moment of inertia for the beam is also indicated there, and a 5 kilonewton load at node 3, and the spans is also given. This part over here is the template I derived in a previous video for a beam element. Basically what this does is you put in the Young's modulus, the inertia and the length, and it gives you the element matrix for that beam. Okay, so let's get to the problem. The 10 millimeter gap just makes the problem a bit longer. Don't be scared of it or anything. Firstly, we need to check if this gap is going to be closed by this applied load. Otherwise, we can just ignore it. So how we do this is we solve the problem without node 2 or without that 10 millimeters and see if the displacement at node 2 is greater than 10 millimeters. Then we resolve the problem with the 10 millimeters in mind, but hopefully this will become more clear as I go on. So with the stiffness method problem, I must first get the matrices or the element matrices for the two elements. So let's do that first, and you will also notice they will be exactly the same. Okay, so the Young modulus is going to be 210 times 10 to the power of 9. That's where E9 comes from, just a different notation. And inertia is 4E minus 5, and the length is going to be 6. So this is going to be our element matrix. I'm just going to make two different matrices as I did in my previous example. So K element 1. So I'm going to copy that. I'm going to paste values. And I'm also going to say this node 1 for element 1, that is going to be V1. The next degree of freedom is going to be phi 1, and then V2 and phi 2. Okay, so and that equal to that. Okay, so there is our element matrix for element 1. This should be clear from my derivational video where or what these values mean. These just indicate the degree of freedom associated with the number in the matrix. V1 is for the degree of freedom V1, or displacement in the vertical direction at node 1, and phi is for the rotation as indicated over here. Okay, so for element 2 this is essentially going to be the same except for the degree of freedom that's going to change. So I'm just going to copy that, paste it, and I'm going to change that because for element 2 it's going to be from V2 phi 2 V3. Sorry, I'm busy with doesn't matter. Make it V3 phi 3 make that the same. Copy, paste, no, transpose. Did that work? Yes. Okay, so these are element matrices for element 1 and element 2. Just to sign my name correctly. Okay, so these are element matrices. So now what I want to do is I want to assemble the global matrix. So I'm going to do that as follows. And the global matrix is usually indicated with a capital letter K. And now I want to order my degrees of freedom in a specific way so that the problem, when solving the problem, it is a bit easier. How I do this is, I'm going to try and explain really quickly. In the solving of such a problem, you will want to have the unknown displacement degree of freedoms first. So that means the displacements or the node that is not fixed in any way. So this is not going to be node 1, because as you can see, node 1, all the displacement there is going to be 0, and node 2 is an unknown displacement, so that is also in for the first round, because we want to check if the 10mm gap is closed. And node 3 is free, so both these degree of freedom is also unknown. So what I'm going to do, I'm going to start off and type V3 is unknown, phi 3 is unknown, V2 is also unknown, and phi 2 is also unknown. And what's left is V1 and phi 1. That's going to be 0. Okay, so I'm just going to copy this and paste the transpose as it was previously. Okay, so now I want to index or assign or compute the correct values to be in this matrix. This means V3 is going to be V3 from this matrix plus V3 from this matrix. And if there is no V3 in this matrix, it's just left out. But how I do this, is Excel has an automated method that makes this a lot quicker, especially if you have a lot of elements. So this is going to be equals if error, then value is going to be VLOOKUP. Lookup value, VLOOKUP stands for vertical lookup again, so it's going to be that value I want looked up in that array for element 1, and for column index number I'm going to say match that value, which is for the horizontal column, and only the top array. Now it is very important that the two arrays start on the same column, otherwise the index that is going to be provided by the match function is not going to be compatible with the index in the bottom array. So just look out for that. My match type is going to be 0, we want exact matches, and it's going to be false for the VLOOKUP, so we also want an exact match. And then for if error is going to be 0. Now that is going to be for element 1, and seeing that element 1 doesn't have V3, this should be 0, and it does, so that's a good sign. Now this whole statement is only for the one element. If I'm going to try and explain it quickly. The if error function I only use for the case when these values are not in the element matrix, such as this, because v3 is not here. So if I just do this without the if error, there is going to be a non-number or non-numerical value, and I can't do, or you can't do mathematical expressions with that. So that's why the if error is there to supply the 0 if it is not applicable, and the VLOOKUP function is there to, well, do a VLOOKUP for the indexing. Okay, also we want to drag and drop this in a moment, so we don't have to type this out for every single cell. So to do that, we must fix some of the arrays. So Excel has a shortcut. You just type F4 and it puts dollar signs in front of the cell names, and this fixes it when you drag it. So just select click anywhere in the cell and just press F4, and you see Excel does the work. And you want to fix both the arrays, and we don't want to fully fix the cells because we want these cells to run down and that cell to run left. And how we do this is, you see the blue cell V3 is always going to be in column E, so we only fix column E by putting only a dollar sign in front of it, and correspondingly for the purple block, or the horizontal degree of freedom, we put a dollar sign in front of the 42, but it's always going to be in row 42. So yeah, that is for the one element. You just select that whole thing, copy, and you say plus, paste, and all you need to do is change the array. So I'm just going to delete that. I'm going to select that array. And again, the other one. This is going to be that array. I'm going to fix them both. F4, 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 and F4. Okay, well that's done. Now we can drag this whole cell. You can drag downwards first if that's what you prefer, it doesn't really matter. And there is our global stiffness matrix. You can do this a lot faster. I just went slowly in the video to try and explain what's going on. Otherwise, I think this might be quite confusing. And one check you can do, if to make sure your global matrix is correct, you can check if it is symmetrical, because that is one of the definitions of the global stiffness matrix. Okay. Nextly, you want to solve the displacements and check if that 10 millimeter is closed or not. So the general equation for the stiffness method is forces is equal to global stiffness matrix, block brackets, global stiffness matrix times the displacements. Okay, so I'm just going to copy this matrix. I'm going to put it over there. That's fine. I'm going to paste links. This is helpful for when you want to change one of the areas of the elements or something like that, so you don't have to copy and paste it again. Equals. And the force vector is the force corresponding to the degree of freedom indicated there. So the force, the vertical force at V3 is going to be minus 5,000 kilonewtons. And that's the applied force. So you can say minus 5,000. And phi3, there is no applied moment, so the moment there is going to be 0. And so forth for the rest of them. And yeah, we don't know what's happening at node 1, so I'm just going to leave that as vertical 1, the vertical action at node 1, and in1, the action moment at node 1. And this is going to be times the displacement vector and some of these will be 0. I'm just going to say place values again. Now some of these will be 0, so let's just go back to our sketch and see what's going on. So we want 0 displacement, so the only place where we're going to have 0 displacements at the moment is going to be at node 1, because it's fixed at node 1, so we just replace phi1 and v1 with 0. And now I want to solve the displacement, so we copy that, paste it there, equals now to solve that you select the correct amount of cells in Excel and type equals MMULT. It stands for matrix multiplication, and I want to multiply the inverse of a part of this. So right, maybe I'm a bit hasty at the moment. Okay, so firstly I'm going to divide up the global matrix. You see the last two rows here is going to be 0. That means these two rows or columns is always going to be multiplied by 0, so they become irrelevant. I'm just going to color them pink. And also in the stiffness method you have essentially two equations, that is the known forces times the unknown displacements. That's one equation, so I'm just going to color the applicable matrix. So I divide my matrix up so I know which part goes where, just a bit easier for identification purposes and so on. And what's left is also seen as one matrix. I'm just going to make that yellow. Okay, that's better. So now, as I were, select the correct amount of cells, type equal MMULT for matrix multiplication. And now I want to solve the unknown displacements. That means I have to multiply by the inverse of the green matrix with the known forces. So how we do that is matrix multiplication by M inverse for the inverse matrix. And I select the green matrix. And multiply that with the known forces. And once you type that, you must press Ctrl Shift Enter, and that gives the displacements in meters, but I want them in millimeters, so I'm going to convert those. That is equal that times 1000. Millimeters. So the displacement at node 2 is going to be 107 millimeters downwards, and that means is greater. I'm going to put millimeters is greater than 10 millimeter, and I'm going to say touches no 2. Okay, so now we have verified that the gap will be closed and that the beam will touch node 2. So now we can do the analysis with the 10 millimeter gap in mind. Okay, now how we do that, we do exactly the same. I'm going to keep the element matrices, and I'm also going to just copy the global matrix, paste it down here. Hopefully this will carry over everything. Yeah, this looks right. Okay, so now what we have is a 10 millimeter displacement at node 2, or vertical displacement at node 2. So this node 2 is now also a known displacement, which means this is going to be at the bottom and the reaction is going to be unknown. So what I'm going to do, I'm going to renumber. So instead of, I'm just going to swap around V2 and Phi2. So I'm just going to put Phi2 and then V2 to get my numbering correct. Phi2 and V2. As you can see, there is a problem. My top degree of freedom names is not carried over from the previous one because I fixed that in the row, so I must fix that quickly. I'm going to go back to the first cell and try and correct that, otherwise I'm working with wrong values. Okay, so I must change 57 to 70, or 42 to 70, sorry. Okay, that should be correct now. Just check it. So it's those two as well as the corresponding element matrices. Okay, that looks right. Press enter and just drag it again to get the correct values in every cell. Okay, as you can see, the values changed a little bit. Okay, so now I'm going to go back to this step where I were previously. I'm a bit lazy, so I'm just going to copy that whole thing again and paste it down here. Okay, so now that I've copied the equation from above, I'm just going to put in the new values of the new global matrix. Copy, paste links. Okay, going to paste that over there as well. Paste values. Okay, so now I'm going to do my boundary values again. we're going to start with the displacement. We know the displacements at node 3 is unknown, and the rotation at node 2 is also unknown, but we know the vertical displacement at node 2 is going to be minus 10 millimeters. It's minus 10 because in a downwards direction, I'm just pointing that out, and V1 and phi1 is going to be 0 due to the fixed point at node 1. And again, the applied force at node 3 in the vertical direction is minus 5,000, no moment at node 3, no applied moment at node 2, but there is a reaction, a vertical reaction at node 2 and the two reactions at node 1. So I'm going to correct my color coding, because this is now a different ballgame, because that is a non-zero value. Okay, so I'm just going to do the color code and then I'm going to try and explain to you what's going on. So, actually need 4 colors now. Okay. That stays green. Make that. Orange. Make that pink. And make that. We're going to make that blue. That looks nice. Can't almost see it, but that's okay. Okay, so what's happening now, I'm quickly going to try and explain the concept where we're going to use to solve the values, because that is a non-zero value. These are not going to be multiplied by a zero vector anymore, so we can't just leave it out. So how this works, this concept is basically, or this formula is basically split into f1, f2, the vector is equal to, okay, if f, okay, if s, okay, is if, okay, is s times d1 d2, sorry, d2. In the textbook or something, you will also see these the force and the displacement vector with f and an s as well, but for this example, this explanation, I'm just going to use f1 and f2. So the kff in this example, I'm just going to color code that as well. That should make it a bit more clear. And the color corresponds to the color in the big matrix, or it's supposed to correspond. Let's see if I can get the correct orange. That one, I think. Yeah, okay. So the colors indicated there is the same as the colors in the big matrix. So for matrix multiplication or something, I'm just going to write the equation for f1 is going to be equal to, okay, if f times d1 plus, okay, if s times d2, and the same if 2 is going to be equal, okay, it's f times d1 plus, okay, it's s times d2. Okay, that is basic algebra, like mathematical multiplication, that row, that column. And so to solve for d1 in this case, that's what we want to solve at the moment, is that vector must rewrite F1. So I'm just going to type rewrite F1. So we're going to say okay, if D1 equal to F1 minus KS times D2. So then to get D1, I'm going to say D1 equal to inverse KF times F1 minus KFS times D2. Okay, that should make a lot of sense because it's just basic algebra. I just rewrote that, took the KFS D2 term over and it becomes negative, and then KFS D1 stays put, and then to get D1 you multiply from the left with the inverse of KFF. Now that is the math that we're going to use now. So I'm just going to select our D1 or unknown displacements. I'm going to copy it down there. Equal. Okay, so now this is the funky part. Let's say equal matrix multiplication. The one is going to be the M inverse of KFF, that's the green part, multiplied by F1, which is that, minus matrix multiplication of KFS, which is the orange part, with that bottom part, which is non-zero. And Control Shift Enter, and that gives us our displacements. And now to get our reaction forces, that is with the F2 equation I've written down, copy that, paste that, and this is going to be in meters, sorry, radians, and type equal signs, and then I'm going to do the mathematics, sorry, equal, and then we do the math, that is equals to KSF, which is the bottom part, sorry, a bit hasty, matrix multiplication of the bottom part, the blue part, KSF, times D1, which is what we did just determined, plus KSS multiplication multiplied KSS, which is the pink part multiplied by the non-zero displacements, and again Control Shift Enter, and that is our reactions. That should be Newton, and Newton meters. Okay, so that's pretty much it. Thank you very much for watching. I hope this example was satisfactory. Sorry for the little math expressions there, but that is necessary knowledge to solve this problem. This is a very descriptive problem and a bit more difficult than my previous, or a lot more difficult than my previous example, but I think it's a very good problem to have as an example and yeah, to go forward with it. Again, this file will be uploaded on a Google Drive, so you can look at it in your own time and check if I made any mistakes. And please ask in the comment section if you have any questions. Thank you very much for watching. If you like this video, please press the like button and subscribe to my channel if you want to see more videos. Thank you.